Okay. David, thank you very much, and Joe as well. Delighted to be here. We're all neighbors, of course. NREL is just down the hill, and I've already run into a few people that I know here tonight that have some connection to the lab, including Mike Lee. Mike, where did you end up sitting? In the back here in our finance department. I want to talk to you a little bit tonight about the sort of global energy picture as we see it, but probably a little bit more about the laboratory's evolving role. You know, those of you who've been in the area here for 30 years will remember that we started out as the Solar Energy Research Institute back in 1977. President Carter came out in sleeting snow and rain around Earth Day and opened the laboratory up. A lot has changed since that time, and I think it's important to sort of bring everybody up to date on some of the exciting new things that are happening there. The world is a much different place today than it was when I started, which was a couple of years later after the lab opened in '77 when I came in 1979. And it's breathtaking, really. This is the most historic moment for the now over 2,000 men and women who are working at NREL in all of the key renewable technologies, and I'm going to talk about that in a moment. For those of you who are not familiar with the lab, NREL is the nation's principal research center for renewable energy and energy efficiency R&D. We are a national lab, much like Los Alamos and Oak Ridge and Lawrence Berkeley, some of the better known and bigger labs, at least better known up until the last few years. And so we do our work, most of our work, for the U.S. Department of Energy as a contract research laboratory. We do a little bit of work with the private companies as well. But I want to talk to you a little bit about how things have evolved over the last 4 years, and I peg that to almost exactly 4 years ago. Some of you will recall that President Bush visited the lab in the February, roughly, of 2006, and it was at an interesting moment. We had just laid off 30 people at NREL when the president came out, and those of you who are responding to that will remember that somehow DOE found several $1 million to bring them all back a couple of days before the president arrived. But one of the things that we talked about with President Bush at that time sort of leads into this presentation, and when he toured our laboratory, he asked some very, very good questions, and the big one for our director, Dan Arvizu, who had just started at that time, was, Dr. Arvizu, be honest with me. What can we really expect for a contribution from renewable energy to this country? And you got to remember that the president was an oil and gas man for many, many years, and clearly came to NREL and to Colorado with some pretty healthy skepticism. And Dan thought a little bit about that before he answered. He said, you know, Mr. President, let me turn it back to you. How much do you want? How much renewable energy do you want? And that answer implies what I want to talk about tonight, which is how critical it is to marry technology, like the technology we're working on, with policies that are consistent and sustainable over time, and markets that will embrace these technologies. Okay? If those things are working together, then the sky is the limit for the kinds of things that we're working on at NREL. So let's go to the first slide. Let me talk a little bit about the sort of global context for renewable energy. You know, we're sort of all in this together now. And so much of what NREL does is collaborative with other countries, both developing world countries where we're trying to help them build capacity for renewable energy in their own countries, the big transition economies, China and India. China in particular, I'll come back and talk about, because they're going to be the big 800-pound gorilla in this market, in this world market. And also the European, the developed countries, the European Union countries in particular. So what you see here is the good news about renewable electricity growth worldwide. This excludes hydropower, which is important to note because hydropower has been around the longest as a renewable electricity option, but is not what we're working on at NREL. We're getting into these other areas. And so you can see that from 2000 to 2008, we enjoyed, you can see over on the right, wind, solar, concentrating solar power, geothermal, and biomass power have enjoyed as high as 27 to 31% annual average growth rates around the world. That's the good news. Let's go to the next slide. Putting that in context is the problem, as you would imagine. If you look at renewable share of total electricity capacity, that is what the capacity is to produce, and you look at the more of the yellow bar versus the green bar. The yellow bar is all those renewables excluding hydropower. So it's been a very small percentage. Impressive growth, okay, but still a very small fraction, around 4% of the installed total electricity capacity in the world. Once you put hydropower in with that, it becomes 22%, much more impressive. Let's move on. So again, just a breakdown, if you look in the, not the column with green bars, but the one to the right of it, you'll see the breakdown of renewables without hydropower from the year 2000 to 2008. And again, that's a 75% growth, but of a very small market to now one that is growing, continuing to grow at a very healthy rate. Next. So where are these markets? You know, it's interesting. A lot of people talk about how the U.S. had the leading world share of the market for renewable electricity and fuels back in the 1990s. Well, in fact, if you look at this, we still do, in most cases, with one exception. So if you go across here, again, this way makes it a bit easier for me. If you look at geothermal, U.S. is the top market in terms of installed capacity. Wind, U.S. is number one. Germany is number one in solar photovoltaics. Concentrated solar power, which is a central station solar technology by which the sun's rays are concentrated to produce high solar flux to produce steam to run a generator. And then biomass power, again, U.S. is number one. So we're continuing to see the market develop in the U.S., and everybody, I think, who studies this agrees that the next big market, once we sort of pull ourselves completely out of this worldwide recession, will be right here in the U.S. And I'll talk a little bit more about that. Okay, let's go to the next.
They cannot see that on this side.
You can't see it?
They can't see it.
Not sure what to do. That's the way this is set up tonight. There may, I don't know if there's any chairs. Oh, for me, moving back.
Right off.
Lean up like that. Okay, can you see a little bit better over here? I apologize. Thanks, sir, for coming up and moving me out of the way. Okay, let's go to the next slide. The other indicator for renewable energy markets is the amount of capital that's being attracted to them. So what you see here, again, is the same trend from this, in this case, 2004. We had a huge 500% increase from the low level of 2004 to 2007 in total global investment in renewable, mostly in renewable electricity projects and companies. It started to stall out as the worldwide recession began in the second half of 2008. 2009, it came down considerably, and I had lunch today with one of the top guys in this space, in the investment space for renewables, and he was saying now as we approach mid-year 2010 is going to be down as well. But there's a lot of prospect for future growth and a lot of money that's now on the sidelines that is likely to move back into this arena. Next. So apologize for the way the screen is bifurcated here, but this is all we have at the country club. Good, that probably is a little bit better centered. These are the kinds of things that the president has brought to the sort of renewable energy arena in this country, and I highlighted the one that has the greatest impact on us, and that is this long term. I don't think it's going to be $150 billion over the next several years, just because of the situation with the deficit. But we're starting to see, for the first time, really since we opened our doors in 1977, a sustained, healthy investment in the R&D. Okay. And I'll show you, I can't remember if it's the next slide or the one after, but I'll show you what that means in terms of how difficult it's been to bring technology into the marketplace because of this up and down nature of the interest in investment in renewables. Let's go to the next one. So again, the first key takeaway that I'd like to leave with you tonight is we can produce all of the wonderful technology at NREL, and it's not going to do a bit of good unless the policies that are there that pave the way for it and that markets are embracing it. So let's move on. From the policy standpoint, you've all been watching, as I have, rather disappointedly, the inability of Congress to produce a comprehensive energy policy. There have been a few key bills passed in the last few years, but the opportunity appears to be fleeting again this year that we're going to see, certainly in the context of a climate bill, but maybe even not a standalone energy policy in the country. And so what that has produced, as you can see on this national map, are state-enacted renewable electricity obligations, or what are called renewable portfolio standards. And these are simply just taking Colorado, which needs to be updated. That's now going to be 30%. What this is saying is that the state is going to require, at least the investor-owned, the big utilities like Xcel here, a certain fraction of their electricity at a future date to be supplied by renewable electricity. This, more than anything else, has spurred the market and the growth rates that I showed you earlier that are global but apply here in the U.S. as well for the renewable energy industry. Were it not for these policies that have been enacted over the past 8 or 10 years, we wouldn't have seen even the growth that the 75% growth from the early 2000s that we're seeing now. So, again, another thing to notice on this map is look at the Southeast. You know, that's completely devoid of any major policy motivation for renewables, and largely because they don't have solar and wind resources that are sufficient there to make the economics work. At least that's the perception. Although there's plenty of biomass power, and I'll show you that in a minute. Let's go to the next slide. Now here's the killer for renewable energy in this country, and it's right here at our own laboratory. What this is a year by year. The bars are the annual funding of the National Renewable Energy Laboratory since its inception in 1977, and you can see what happens with the change in administrations. This is a very politicized game that we are in, and so we, as quickly as we ramped up in the late 70s with President Carter, we came down just as hard in the Reagan years. Largely, not a lot of people think because President Reagan didn't embrace renewables, that was part of the reason, but the bigger reason is that in the early 1980s, you'll recall, world oil prices plummeted. And the interest in renewables flagged, and then of course it came back up as oil prices started to rise again in the Clinton years, and you can see what's happened in the last few years. If you overlay the annual average world price of oil on this graphic here, you'll find it in very close agreement. So that's what it's saying, is that, you know, we live in this boom-bust cycle, and that has consequences. I like to tell the story of back in the early 80s, we had a guy working at NREL on what are called polymer solar cells, which is a solar cell that is made out of a polymer material. It's basically like a plastic. And because of the polymer instead of some of the really hot, the very expensive silicon materials that we were using at the time, it had great promise for being a game changer in the marketplace by lowering the cost of PV. When all the layoffs occurred at Siri at that time in 1981, Alan Hager was the guy's name. He left. He didn't think there was a future in this stuff. And 5 years ago, he won a Nobel Prize in photoelectrochemistry for this kind of work. So, you know, just think if he had been around here and been able to really pursue this investigation on something that could have been so, groundbreaking. And that's what you need. That's why you need this sort of very steady state investment in science and long-term science and technology. And you can see, of course, and I'll break this out in a minute, the last few years we've had this growth. The yellow represents some of the Recovery Act, the funding that's actually come into the laboratory as well. And our staff, again, for the first time, just a couple months ago, passed the 2,000 mark. Okay, let's go to the next one. So where are we investing in renewable fuels and electricity today? This gives you an idea. If you start with the blue piece of the pie up there in the upper right, that solar energy has been the largest investment, both the photovoltaics, the solar cells that are typical for residential applications, and then these concentrated solar power towers and other type devices for utility scale power. Biomass and biorefinery systems. Biomass meaning organic materials like wood waste and agricultural waste and forestry waste that can be converted into fuels or electricity or high-value chemicals. We've done a lot of work there. I'll talk about it in a minute. Wind and hydropower, but mostly wind, has been, some of the leadership here in the country really has been in wind energy at NREL. Building technologies, how do we take buildings and make them more energy efficient? That has been a big focus, though a lot of people assume that because we're called a Renewable Energy Laboratory, we don't do a lot of work in efficiency. That's not true. Both vehicle technologies and buildings and industrial process energy efficiency is a big part of what we do. So that's kind of the breakdown. Let's go to the next one. So one of the things that we constantly have to do, it's fine to put a pie chart up and say we're going to spend $70 million this year on solar. The bigger question for getting renewable energy to get past that 4% mark and make some meaningful contribution to our primary energy demand is to make sure that we're doing research in the short term, but also in the long term, okay? And the short term is important because it's really working with industry, and I'll show you what that means in a minute, to get current technology, current generation technology into the marketplace faster. But while we're doing that, and this is a story we constantly have to tell Congress, they're all about, what are you going to do tomorrow or in the next 2 years? We are saying you've got to make equal investments in the mid and long-term technologies. The long-term stuff, which we view as revolutionary, we don't even know about today. It's kind of like these polymer solar cells that Alan Hager was working on. We're never going to get to 10, 15, 20% or 30% contribution from renewables unless we put an equal amount of investment in the revolutionary and disruptive technologies. Let's go to the next slide. So what am I talking about? In the near term, you can see one of the things that we do here to kind of remove barriers and broaden deployment in the marketplace today is that we've developed a lot of tools at our lab, and just one of them here that you can sort of see, and I'll show you what it means, is we've done all of the mapping of the renewable resources in the U.S. and much of the renewable resources around the world at NREL. And we've done it with these computer-aided graphics that can show at a gross level where the best resources are. You clearly, once you find that, you've got to go to a particular place and do some good prospecting. But this has been a hugely important tool to build capacity in other countries. Let's go to the next slide. So what this does is you can start to build and see what the renewable resources look like. David, just page down through here, and I'll just explain that. Just go to the next one. So here, we're building here. All the yellow is where you get good photovoltaics, good sunlight for photovoltaics, solar cells to convert sunlight to electricity. In the red, which tends to be in the southwest, as you'd expect, these concentrating solar power facilities. The blue is the wind, of course, and again, the upper Great Plains. And increasingly, of course, the holy grail for wind is really offshore. And I'm not talking necessarily about off Cape Cod. I'm talking more about maybe off Louisiana and Texas and up the California coast, where they see a lot of oil rigs these days and are not as likely to be in opposition to wind turbines out there. And by the way, I'll come back and talk about what we're doing in that. Okay, let's go to the next one. Biomass. Okay, so again, remember that hole in the southeast for these renewable portfolio standard states. Biomass is found everywhere, whether it's forest or agricultural byproducts. And so the key for trying to drive this market more evenly across the country is developing biomass resources in the southeast particularly. But there's plenty of resource there, as our maps indicate. Let's go to the next one. Geothermal, the geothermal resources tend to be concentrated in our part of the country, in the western United States, but you can find them in other places. Next one. Hydropower, again, something that we don't work on too much, but there are resources. And then lastly, or second to last, it's really nice to be able to say where the resources are, but where's the transmission, where's the grid to move those green electrons to the big load centers in the country. This is where one of the next challenges that I want to leave you with that we're facing is how do we get the kind of infrastructure, and it is a huge investment, to move green electrons from North and South Dakota to Minneapolis or Milwaukee. Okay, so that's the other side of the coin. Good technology, lowering technology risk, have to be able to move the electricity or the fuels, the alternative fuels. And this grid shows you the challenge of that. Okay, let's go. And let's just move on from there. That's just an aggregation. So in the midterm, there's a couple of facilities. A couple of you were up at our National Wind Technology Center today. Or have any of you been there besides the two people I talked to? Outside of Boulder? Good, okay. This is the world's most sophisticated and largest wind turbine technology center. And the fellow in the upper photo there is standing in front of a dynamometer test facility. And what that is a facility that a big wind turbine manufacturer can bring their drivetrain. And you can't really get a good feel for the scale of these things. So this is a 2.5 megawatt dynamometer that they can hook up their drivetrain from their turbine and run it on our dynamometer, and we can get in 2 months a simulated 20-year operation of that drivetrain. We can do the same thing with blades at our blade test facility. So the testing that is needed at NREL to get us into sort of the midterm technology, get it field validated, it's on the drawing boards now, but to get it out there and understand how it's going to do in the real world is another big part of our mission and why it's so important to maintain at a consistent level. On the bottom, we have, for those of you who come out and see us, we have a new photovoltaic research laboratory. It's unique in the country. It uses a lot of robotics, which is what you're seeing here, that can take cell samples and move them through a 6-bay research facility such that we can have 6 industry partners working with us simultaneously. That creates some synergy between the industry partners. They may start looking at each other's technology, and we start to see an awful lot of exciting new opportunities there. So again, partnering facilities with the laboratory help us in the midterm. If you go to the next slide, in the longer term, we're starting to look now at how do you get down to if it's biomass, if it's plant material. Can we get down and look at the molecular and atomic level? What creates plant resistance to breaking it down into simple sugars to ferment into cellulosic ethanol in this case, but into other alternative fuels? We've never had that capability before. We have it now. You can see it's 3D. It's pretty neat 3D stuff. You put the goggles on, you see all these things kind of coming at you. But it's again, it's the kind of tool that we need to understand next generation technology, what it's got to look like, how it's got to be made up, and in this case, how we can break it down more efficiently and therefore at less cost. Let's go to the next one. Just a quick mention about, before we even get to new alternative energy supplies of electricity and fuels, we try to answer the question, how do you reduce your energy appetite, your energy bill, in buildings especially? And so what we're concentrating on here is looking at building systems, and especially new buildings, commercial and residential buildings, in a much different way than we have in the past. And so just a quick example, we provide design tools, computer-based models for architects to use to design commercial buildings at a fraction of the energy cost. They can do the trade-offs between cost and energy savings and look out over the life cycle of the building and all the payback requirements and do this sort of thing. So it's not just coming up with the next nice glazing for windows or something about LED lighting. It's also giving architects and builders tools to actually apply this stuff. We do a lot of that at NREL. Next slide. Let me talk a little bit about electricity supply. Let's go to the next one. In terms of wind, of course has been the big success story around the world, and certainly in this country. Remember that we have the largest amount of installed capacity now, and that's because we've been able to get the cost down. When we opened our wind program at NREL, the cost for generating a kilowatt hour of wind power on a utility scale machine was about 80 cents to $1 per kilowatt hour. Today we typically can do it at good wind sites, tend to be at least 12, 15 mile per hour annual average wind speeds at 6 to 9 cents. The goals, when we come down and talk about the goals here, are to actually try to cut that in half to about 3.5 cents for onshore at lower wind speed sites, and then 7 cents offshore. We think the first offshore wind installations, including the one that looks like it's now going to go into Cape Wind, is going to come in closer to 10 to 12 cents a kilowatt hour. But we think we can get there, and you can see pretty quickly for offshore, and 3.5 cents in the next couple of years. By the way, these are unsubsidized prices, or unsubsidized costs. These would be without any production tax credit or anything. So, and I love this picture here because for those of you who haven't been up close to a wind turbine, you can see the scale of these things. That's just the nacelle where the rotors turn, or the hub where the rotors turn. So we have done a study at NREL that basically says that we know how to get to 20% of our electricity needs from wind by the year 2030. And it's a huge challenge from a technological standpoint, but also for the reasons of infrastructure and consumer acceptance and a lot of other non-technical reasons. But that's the kind of thing that we look at on the analysis side of NREL. What can we, answering President Bush's question, what can we actually count on over the next coming decades? Let's go to the next one. So you can see some of the things we're working on. Offshore wind, we're doing some model development with MIT on what happens when you move these turbines that are just sitting there rigidly on shore and move them into, especially in a deep water environment like these oil rigs. And for wind turbines, you know, they're getting enough buffeting when the blades are going around in turbulent wind. If they also start getting tower, you know, structures that are going like this, we can't operate effectively in that kind of a regime. So we're trying to figure out how do you, we know how to do this in shallow water, 30-meter water. We can get them, you know, guide and anchored to the ocean bed. But if we really want to get them off the horizon, which gets us outside of the Cape Wind issue of the aesthetics and visual pollution, we're going to have to be able to site them in deep water. Innovative tall towers, the higher up you go, the better the wind is, the more consistent and smooth it is. So, you know, can we get up higher without a huge additional cost penalty, and with the same structural integrity? Advanced blades, we're always looking at trying to find blade materials that are both lightweight and therefore less costly, but durable. They'll hang in there for doing millions of cycles over 20 years in a tough wind regime. And then again, wind forecasting, I'll come back and mention that here as we wrap up. That has become now critical as we look at higher penetrations of renewable electricity that utilities are going to incorporate on their grid. Next one. Concentrating solar power and photovoltaics. This is where the lab really started as the Solar Energy Research Institute. You can see what the status of the marketplace is in the country and why we don't have a whole lot, just barely a gigawatt of installed photovoltaics, almost entirely on residential roofs and the sides of buildings, and in some cases in window technology. It's 16 to 32 cents a kilowatt hour. Okay, that's well off the market in most places in the country. Concentrating solar power a little bit closer to the market. You can see what our goals are here again in the next few years to get to the 6 to 13 cents for photovoltaics and 8 to 11. I think if we can get below 10 cents a kilowatt hour for concentrating solar power, the market, for example, in California, at least the utilities out there tell us, will open up massively for concentrated solar power. And let's go to the next slide, and I'll mention what some of the research issues are. For photovoltaics, it's all about the materials. You know, how do we find new combinations of these real thin film materials that essentially can be applied like a very thin coating of paint to some substrate and improve their efficiency. Today, if I put a thin film product on the roof of my house, it's only going to produce about 7 or 8, maybe 9% efficiency by which it captures sunlight and converts it to electricity. Whereas the silicon products that have been out there for a long time produce power at about 20% efficiency. So somehow we've got to get that efficiency up, and then the thin films, which are much cheaper to make, and we get off of the issues about processed silicon and competing with computer chips for that feedstock. We move on beyond that. So concentrators, absorbers, there's all kinds of things. We've been working with inkjet printing technology. You know how you apply ink to paper with the old inkjet printer. That offers a very interesting and low-cost way that we may be able to find to lower the costs on photovoltaics. Concentrating solar power is, you know, when you've got the sun during the day and you're producing this high temperature flux to produce power at a central station generator, what happens at night? Okay, and so in order to firm up the value of that power, we're needing to figure out what kind of medium we can use to store that heat overnight, so that we can continue to produce power at least for several hours beyond what we can today. Let's go to the next one. And then just a quick note about biofuels. This has been a big focus for the laboratory since day one. We've been working on cellulosic ethanol, which is, don't take the corn kernel, which competes with food. Let's take everything left over after you take the corn kernel and convert it to ethanol. You can see what the market is in the U.S. today. There's about 175 companies producing some form of biodiesel. And then corn ethanol, which dominates the market at the moment. There are about 200 commercial plants. We're really in a transition there, I think, for reasons that ought to be obvious to everybody in terms of this sort of, in some ways, surprising issues that have come up around the life cycle costs of producing ethanol, not the least of which is water. For every gallon of corn ethanol produced, you need 3 to 4 net gallons of water. That doesn't work well, especially in an arid climate like we have here. So we're trying to find cellulosic ethanol as the next generation biofuel, and there are plants that are moving ahead in this country, including Range Fuels, based here in Colorado, that's opening a plant in Georgia here in a few months. At least that's the hope. So marketplace has affected this business considerably. Okay, attracting capital to a lot of the biofuels companies has now become a major issue. So we're going to see if we can if the economy moves quickly enough to get us out of that danger area, but time will tell. Let's go to the next one. There are the goals. Again, we're trying to get, now what we're saying here, in a couple of years, we hope to have cellulosic ethanol conversion technology at a cost that's competitive with gasoline. Okay, so that's a big stretch. We've made huge progress over the last 15 or 20 years, but that's what we're trying to do. And then there is a renewable fuel standard in the country that basically says, let's try to have 36 billion gallons of renewable fuels by 2022. And you can see a large component of that 22 billion, as we get off corn ethanol, needs to come from cellulosics and other alternative fuels. That's what we're working on: cellulosic biomass conversion, some new biofuels, algae. Some of you asked me about algae. Algae has great promise because it offers the beauty of higher yields, but the cost is still well off what it needs to be to create a major market for that. And then biofuel sustainability. What are the real costs when you produce a biofuel from beginning to end, not just what your conversion cost is? Next slide. And go ahead to the next one. So let me sort of end up here with a couple of things about what's also different from even 4 years ago when President Bush visited, and certainly from 1977 when we opened up. The lab has typically been a technology innovation outfit, meaning we've largely just had scientists and engineers that are creating technology. Now, because so many of these technologies have begun to emerge and have matured, we really need to focus on how do you move that technology into the marketplace. And our view is that the purest form of technology transfer is working with industry partners. They can sit down with us right at the beginning and say, okay, here's what we think we can do in terms of turning your technology into useful products that we can sell and make a profit from. So you can see how that's changed things. We now have 350 or so active industry partnerships in every state in the country almost, okay, and some overseas where the conditions are right. We have more. These CRADAs are cooperative research agreements in which a company will work with us. We don't write them a check. We will both bring intellectual property to the table with our experts, work on it, protect their IP for up to 5 years, and then it all becomes public. That attracts people like DuPont, who we just finished some work in helping design the first biorefinery for DuPont, which is going to be helpful to DuPont, but it'll be great for us because we've learned so much more about the design requirements for the entire industry that wants to go from petroleum to biorefineries. And then the other interesting thing, people ask me a lot about how much of your intellectual property, your inventions and whatnot, go out there and get in the marketplace and produce a source of revenue. 70% of the lab's solar portfolio is licensed to private companies. So it's another good measurement for us on how we're doing. And then a new technology IP portal. If any of us in here wanted to form a new thin film company, we had a technology we've been working on, but we were sort of curious about, is it already out there and who's been working on it and are there patents for it? And now, instead of having to contact the lab or come to the lab or one of the other national labs that works in the area, we have a portal that's available on the DOE website where you can go and you can actually say to the website, take a look at cadmium telluride thin film technology, and it'll pop up all of the IP for that, and so you can quickly bundle your search into something that will tell you exactly what your company is wanting to find out. So that's kind of where we're going. You can see some of our partners. They're as small as Heliovolt. They're as big as Walmart. We've done a lot of work with Walmart. I was kidding our folks at lunch or at dinner tonight, and there's a lot of talk about the smart grid, about utilities being able to talk to individual customers as opposed to seeing what's going on at the substation. The guys at Walmart say, we've been doing that for years, for 10 years. And I said, well, what do you mean by that? And I said, well, if somebody in the Aurora superstore leaves a door open to one of our food freezers, a sensor goes off in Bentonville, and we call them up and tell them to shut the damn door. That's our smart grid that we've had long before this became fashionable. Okay, let's move on to the next one. And then, again, I'm not going to dwell on smart grid, and there's a lot of talk about it. We'd like to talk about it in terms of the smarter grid. We don't think we're going to see a smart grid here for a number of years because it's a very complex set of issues. Some of you may have seen the article in the Post this morning about privacy being violated by all these utilities being able to see what's going on with respect to appliance use in your home. So there's a lot of stuff that has to be done. We're right in the middle of it in terms of coordinating all of the DOE work that's going into smart grid. And the next slide will show you the next major research facility that is going to go on our campus. We're really excited about this. It's called the Energy Systems Integration Facility. This is an artist's rendering of what it will look like. But this will enable utilities in the United States for the first time, instead of testing higher penetrations of renewable electricity on their own grid, they'll be able to model their grid and their load at NREL in this building. And they'll be able to walk through all the operating algorithms, the changes in load following, the forecasting issues from day to day for wind and solar at NREL. So in 2 years, we'll see a unique facility in the world coming up at NREL to do that sort of thing in terms of, and also for the smart grid. What happens when you've got 1,000 of your customers that are now talking to you about their energy usage, and oh, by the way, maybe plugging in plug-in hybrid electric vehicles in their garage to your grid. Let's go to the next one. This we are extremely proud of. This is an artist's rendering, though you'll see in a moment that it's almost done, of what we think is going to be perhaps the most energy efficient office building in the world, our research support facility. We're going to move 800 people in there, and just to kind of give you an idea of why this is such an incredible building. This is about a 220,000 square foot office building. And a typical building of that size and purpose in Denver would use about 90,000 BTUs per square foot per year. This building will use 30,000 BTUs per square foot per year. So, and it's got a lot of, I don't have time to go through all the neat aspects of this, but it's going to be an extraordinary building. It will create a different culture for people that we're a little nervous about, because in order to get light into these buildings, one of the things you have to do is everybody can't be more than 30 feet from a window, and cubicles are going to be 3 foot high. There'll be no enclosed offices, because we need all the light and air in there to make these office spaces 100% daylit. So yeah, so you can, just that reaction shows you we're trying this out on a few guinea pigs up in another office building in that environment. And we had a great photo of a bunch of guys who were standing at a cubicle talking, which is kind of what we wanted to encourage with this. And then one other guy sitting back in front of this computer looking a little anguished because he's listening to these guys talk. So we'll see what happens. Let's go to the next one, and I'll show you just one feature of the building. Here it is under construction down here below some of our existing facilities. But one of the simple things that we did, and by the way, instead of, NREL as the National Renewable Energy Lab has to walk the talk. Our campus has to be a showcase for what's doable in the world, and that's what this building is all about. So one of the things we did, instead of going out with 2 contracts in sequence, one for an architect to design the building, then we have a design, we turn it over to a contractor. We said we want a team to bid on it, and so we picked what we thought was the best team of a architect and a contractor to come in and sit down at the same time. And we told them, here's how we want this building designed from an energy standpoint to make it happen. And so now the builder is building a design that he was in on right from the get-go. One of the things we did, instead of creating a monolithic building, just a rectangular building, we opened it up. We had enough footprint to do this. We opened it up into 2 wings, and you can see what that did. This is sort of south coming this way. It takes advantage of sunlight for both wings. Okay, so the south wing and the north wing get sunlight at almost all year for the 100% daylighting that we need. And there's some other interesting features, one of which is some of the structural columns in the place are old recycled natural gas pipes. Okay, we love that. We love that sort of symbolism. They were just laying in some natural gas yard down in Texas, but because there's a little bit of corrosion, they can't use them anymore to run stuff through them. But they're structurally, completely complete integrity. So they're now holding up this renewable energy office building in Colorado. Okay, let's go to the last slide. So that's basically what I wanted to talk about, and that is to sort of end on a theme that is really important to us. We know that a lot of us, especially the guys that are my age, have been around a long time, aren't going to be around to hear the thanks of people that appreciated what we did here in the community and what we did in the world. But we're bound and determined to do it, and we have this incredible mission. We're attracting the best people in the world. We have 56 countries represented in the workforce at NREL. It's an exciting time to be there, but this is what it's about. And with that, I think I'll stop.
Can you comment on the status and the outlook for the dozen or so CSP projects out in California, Nevada, Arizona?
Yeah, well, only to the extent that the projects that we're familiar with and have actually participated in to some extent, or at least early on in some of the technology that's being used. I think most of them are moving ahead okay, not all of them. And, I'm sorry, I should repeat the question. The question is, what is the status of around a dozen concentrating solar power projects? Again, where there's either a point focus with mirrors and reflectors to create high steam, or you run a medium through a trough. In California, probably also in Arizona, where there's also some activity. And they're moving ahead. You can see that the projected marginal cost for these new projects is pretty close to the market, especially in California when it's competing against a higher residential retail rate. But there are some that are, as other renewable projects, have run into some capital issues, capital financing issues. So I want to be clear on that again, these projects are as vulnerable as any other major projects in the country, energy or otherwise, to capital formation and finance. Even T. Boone Pickens, we were talking about T. Boone at dinner, his big idea about marrying natural gas and wind he's kind of had to put that on the back burner as well. But anyway, that's what we understand. And again, the big race there is trying to solve getting longer-term storage for concentrated solar power.
We're over on this side.
Okay.
Do you see the need for backup systems in places like the Northwest?
Do you see a need for backup systems in the Northwest?
Backup to renewable energy power projects? Absolutely. I mean, you see the need for that anywhere because, these are intermittent variable technologies. And let me tell you one of the things that we're doing to try to solve that issue, which is rather unique, and we're doing it with Xcel Energy. When XL, at one of its wind farms, calls up the wind farm operator and says, we've got all the power we need, but the wind is still producing. We don't want to dump that power. We don't want to shut down the turbines. So what do? Okay. So what we're looking at, and we have an experiment underway at our Wind Technology Center, is let's take that power, instead of shutting off the turbines, let's keep producing wind power. And instead of putting it into the XL grid, let's run it through an electrolyzer, which is a piece of equipment that is water, basically. In the presence of electricity will produce oxygen and hydrogen. And we take the hydrogen from that wind power produced system and compress it into a fuel cell, and then run it back out as electricity or fuel at the site, but as electricity back into the XL grid when it needs it. And that has the effect of firming up the power value of wind. Now, as you might guess, because of the sequence of the steps in that process, it's pretty inefficient at the moment and therefore very costly. But we're making progress there, and that's one of the new ways, along with things like pumped hydro that they use in the Northwest, to try to deal with that intermittent nature of these renewable technologies.
I think you're on your right. Thank you. This has been fascinating and very, very interesting.
Thank you.
I'm curious about the office structure that you're building. How do the qualities that you're putting into that translate to, say, New York City, where you don't have a large footprint? You can't necessarily take advantage of sun and being able to do a optimal placement of building.
That's a very good question. The question has to do with, here in Colorado, and given the footprint that we have for this new office building, with all of Colorado's sunshine and the amount of space we have to capture sunlight and do a lot of other things, when you compare that to, say, a big high-rise office building in the heart of New York, what are they going to do? How do you retrofit a building or even build something new that doesn't have that kind of footprint, that doesn't have the access to sunlight for a full day because of the cavern it sits in? One of the things, there's a very interesting building in New York City. You can Google this online. I think it's called 4 Times Square. And the south facade of windows on 4 Times Square, about not the entire facade, but about at the 30th floor up, where it gets sunlight for most of the day, has a thin film solar product on the window. They're producing a lot of the power in their building from these building integrated photovoltaic devices that actually eventually will become a glazing on a building. Now it's actually something that's applied to it. So there's different ways to think about what you do in those kind of environments where you don't have access to the kinds of resources we do. The other thing is just switching out your lighting, to compact fluorescent lighting or eventually LED lighting. So retrofits are much, much harder to deal with, and certainly in a big city where you're kind of, surrounded by structures that are going to block everything for you.
You mentioned that China was the 800-pound gorilla on the international scene. Could you go into more detail?
Yeah, this is an interesting paradox, I guess, if you will, for China. China, of course, as a lot of people, I think, were mentioning tonight, is building coal power plants at a breathtaking pace, one every few weeks, I understand. At the same time, they are trying, in something of fits and starts, to introduce renewable electricity in the country. We're actually helping them under a bilateral agreement with the U.S. State Department and DOE in rural electrification for their countryside with solar and, in some cases, wind. So they're moving in that direction. They have set a national renewable portfolio standard of, it was 20%, they backed it off to 15% recently. So they've set a goal that they're moving at a somewhat slow pace. On the other hand, and the paradox is, when, we spent a lot of time over there, and they are building their photovoltaics manufacturing industry to the point that our guys feel that in the next few years, of the 10 biggest photovoltaic manufacturers in the world, 7 or 8 of them will be in China, or at least in Asia. So, again, here, they're looking at this now as another way of job creation and economic growth, and how much they make their own market in the country is up to a lot of other political and policy considerations. But China is going to be a major, and probably the major player, in residential photovoltaic markets around the world here in just a very few years.
There seemed to be a contradiction in all the information you showed us. Early on, at one point you showed us a pie grid that suggested that 1/4 of that pie was solar energy. And I was left with the impression, whoa, solar energy is substantially greater in this country than wind, for example. But then when we got toward the end of your presentation, you seem to be showing that wind power is growing faster or has a bigger share of the market. What am I missing?
No, it's a fair question. Did everybody hear the question about sort of the contradiction between solar and wind? There are two different sets of issues that are reflected by the maturity of each technology. Solar, as I indicated, is way off the market in every type of technology, at least in the photovoltaics area. And so our goal there, and why we're spending a lot more money there, is to try to accelerate the pace at which second generation or photovoltaic materials, polymers, nanomaterials. Let's try to bring lower cost, high efficiency solar into the marketplace a lot sooner. In part because we have a much bigger, broader solar resource in the country than wind. Wind is this seasonal, temporal. Solar is out there during the day, every day, at least in the good regimes. So the portfolio of research that we have, the investment in that research, is dictated by where that technology stands at any given time. And so in the case of wind, we now have wind power that can operate at a competitive price in many parts of the country. The question now is, how do you get it to a competitive price in areas where the annual wind regime is much lower? We've developed most of the good sites in the U.S. And those wind regimes tend to be lower, but closer to the big demand centers. So we're working on, let's make the next generation of wind turbines cost less and have a higher efficiency by which those blades capture the wind.
I think we have time for one more question, and maybe we'll have to restate it because we'll have trouble
Oh, I'm
with
sorry.
our portable mic.
Okay.
Last question.
Colorado State University, up at their engine lab, is doing some work with, and I believe it's Holland, where they've got various different types of energy, but they can't tie together in their grid, and they're working to put the grid together. I understand someone from Enron was working with them also. Is that Holland? And is it true that Holland has enough of these various together to produce their own energy, except for right now they're selling the excess to Germany? Is that something that...
I think the question has to do with some work being done at Colorado State in their engines lab using some technology that has been developed in Holland that I think you're referring to, maybe either combined heat and power or district heating, which Holland is pretty well. No, something else.
Actually, they've got several different things. They've got power generated from waves. They've got power. Some of it's nuclear, but they're trying to get away from that. But they've also got wind power, and they've got various different power setups, and they don't have a grid that can sustain it.
Well, then,
so
okay, I
the
see.
engine lab there has a duplication in miniature of their control set, and they were working with Emerald to get some of the things that Emerald is best with. But is Holland actually that close to being self-supporting?
I don't think so. I don't think any, there are a few countries that are that close. The biggest wind producing country as a percentage of overall electricity in the world is Denmark, and that's about 25% of their electricity. But every country, Holland's a good example of most countries in the world. They're trying to understand what their resources are, what technology they have, and where they have gaps, they're going to go somewhere else. Holland's collaboration with Colorado State is a good example. Our collaborations with the Fraunhofer Institute in Germany is another one. Where can we get smart by working together collaboratively? And I didn't touch on that very much, but the last thing I'll say is that in addition to these several hundred U.S. partners that we have, we're very active in countries around the world. We're very active I've mentioned in China, but even in Brazil, for example. We're trying to understand, Brazil gets half of its fuel from ethanol from sugarcane. They've made that work down there. So, what can we learn from each other? It's a very collaborative game, and we see that as a very important part of our mission.
Thank you very much.